In example 4, we are looking at 6 different groups and we are trying to determine if any pairs of groups are isomorphic or not. So if you haven't done so already, stop the video and try to figure this out on your own. And then come back and see if your reasons agree with the reasons I'm going to show in this video. Sometimes there are multiple different solutions possible. I started by writing out the groups. And the first thing that you may notice is that we have order 4 groups and we have order 6 groups. So the order 4 groups are Z4, U5, U8, and U12. And the order 6 groups are Z6 and S3. So the very first thing that we know about isomorphic groups is they have to have the same order. So if there's any chance of any groups to be isomorphic, they have to be order 4 or they have to be order 6, but they couldn't be across those orders, I'd be isomorphic. So let's look at the order 4 groups. Let's look at these first. One observation that you may make is that Z4 is cyclic. So if any of the other groups were cyclic, then it would have to be isomorphic to Z4 because all cyclic groups that have the same order are isomorphic to each other. So let's look at U5. Is U5 cyclic? Well, there's only one way to find out. Let's take an element and let's take powers. So I'm starting with 2. 2, 0. 2 to the 0 is 1. 2 squared is 4. 2 cubed, that's 8, mod 5 is 3. And I forgot 2 to the 1. 2 to the 1 is 2. So by taking powers of 2, I actually found all my elements in U5. So U5 indeed is cyclic. 2 is a generator. 3 also is a generator if you wanted to keep going, but 1 generator is enough. So U5 is cyclic, and therefore Z4 is isomorphic to U5 because they are cyclic of the same order. Okay, yay! So we found 2 groups that are isomorphic to each other. What about the other 2? What about U8 and U12? And to help us with that, I already made Cayley tables for those 2. So that can help us work through this a little bit faster. So if you are comparing those 2 Cayley tables, if you're looking at the Cayley table for U8 on the left and the Cayley table of U12 on the right, what do you notice? They look very similar, don't they? So we can, just looking at it, it's like 1 plays the role of 1, 3 plays the role of 5, 5 in U8 plays the role of 7 in U12, and 7 in U8 plays the role of 11 in U12. So these 2 groups are isomorphic to each other. U8 is isomorphic to U12. We kind of see it in the structure of the Cayley table, but we can even write down the isomorphism. So we can say 1 gets mapped to 1, 3 gets mapped to 5, 5 gets mapped to 7, and 7 gets mapped to 11. And really, if you had the Cayley table for U8 over here, and you just replaced 1 with 1, 3 with 5, 5 with 7, and 7 with 11, you would get exactly the Cayley table over here of U12. So there we see our isomorphism. Okay, so now the question is, could we we have two pairs of isomorphic groups. We have Z4 and U5, and we have U8 and U12 being isomorphic to each other. Can they be isomorphic across those two sets? So is it possible that Z4 is isomorphic to U8, let's say? And for that, it's handy to actually be looking at the powers of 2 and to be looking at, actually, let's just think about Z4 and U8. Looking at the Cayley table, one thing that is striking, every element in U8 is its own inverse. What about in Z4? So in U8, we have 3 elements of order 2. We have 3 squared as 1, we have 5 squared as 1, and we have 7 squared as 1. So we have 3 elements of order 2. What about in Z4? In Z4, only 2 plus 2 is equal to 0. So only 2 plus 2 has order 2. And so since we have 3 distinct elements of order 2 in U8, but only 1 in Z4, they are not isomorphic. So Z4 and U8 are not isomorphic to each other. And the writing right here, looking at the elements of order 2, that is the reason for that. But so if Z4 isn't isomorphic to U8, then Z4 also isn't isomorphic to U12, and U5 isn't isomorphic to either of the other U's either, because it was isomorphic to Z4. So we found all isomorphic pairs, U8 and U12, and Z4 and U5, at least among the order 4 groups. Now let's go back and look at our order 6 groups. So let's look at, what is it, Z6 and S3. So what about Z6 and S3? They are definitely not isomorphic. And there are many, many reasons. So one reason is Z6 is cyclic and S3 is not. Another reason, and that is, we actually can write down what that theorem is. That was theorem 6.3.2. Another reason is Z6, is abelian, and S3 is not. And that is theorem 6.3.1. There are other reasons. You can also look at elements and orders of elements, and you'll find that in Z6 you have only 1 element of order 2. But S3 has a lot, right? All the 2 cycles. So we have 3 elements of order 2. And you can probably come up with more reasons than that. So we did it. I think we looked at all pairs of groups and figured out if they were isomorphic or not. So the 2 order 6 groups are not isomorphic, and then among the order 4 groups we found 2 pairs that are isomorphic. If you want to look at this in more detail, the notes are really nicely organized. So if you're looking at the solutions in the notes, you can read through the reasoning in a little